Thanks. And I want to thank the organizer for inviting me. Today I want to talk about a theory called Dirac spin liquid and establish that in two cases, one on square lattice and the other on Kavli lattice, that it serves as a quantum critical point. So this is work in collaboration with my postdoc supervisor, Sento, and his student, Yunchao Zhang from MIT. The outline of my talk will first have a brief introduction to Dirac spin liquid, which was also mentioned in previous day's talks. I'll mention that a connection on square lattice between the Dirac spin liquid and the D-wave superconductor. Next, crucially, we'll discuss the Dirac spin liquid described by quantum electrodynamics in 2+1D, perturbed by a monopole operator and its kinematics, the symmetries and anomalies, etc. Then we'll argue that for square lattice antiferromagnet, Dirac spin liquid actually represents an unnecessary quantum critical point, a unnecessary phase boundary inside the ordered phase on square lattice. And if time permitting, I'll mention the Dirac spin liquid theory on another Kagome SU3 magnetic system. We probably don't need to go over the construction for a frustrated magnetic system. So the spins are fractionalized into spin-ons, and for spin 1/2, we have two spin-on species. And the spin-spin interaction at mean field level can be decomposed into a quadratic mean field Hamiltonian in terms of the spin-ons. And the Dirac spin liquid is realized when the spin-ons are hopping in a certain pattern described by this nearest neighbor hopping Tij. Another ingredient is that this mean field is invariant under a U1 phase rotation, both on the spin-ons and on the hopping matrix Tij. So to go beyond the mean field, we need to include the U1 gauge fluctuations. Dirac spin liquid can be realized on a plethora of 2D lattices. And here, for example, we showed on square lattice and on triangular lattice with certain hopping pattern. So on square lattice, it's called the staggered flux pattern. When the spin-ons are at half filling, as imposed by the physical Hilbert space constraint, the spin-on dispersion, each spin-on species will have 2 Dirac cones. So together, low energy will have 4 Dirac cones. Like each spin-on will have 2 valleys, and together we have 2 spin-on species. And they couple to the U1 photons. So it's described by the quantum electrodynamics. And there is an emergent symmetry group, which is SU4, that rotates between the 4 Dirac fermion flavor. There is also a U1 flux conservation that's associated with the total, the conservation of the total flux of the small a gauge field. It is shown that in numerics that this theory has an emergent conformal symmetry. It flows to a CFT. This large N results continue to hold for the physical case where we have 4 flavors of Dirac fermion.
In the square lattice case,
yeah.
How do things depend on phi? Like
right.
Standard flux space, does it depend on phi?
The longest scale physics doesn't depend on phi, to my recollection. At particular, when phi equals to pi, there is some enlarged gauge group, like to SU2. For generic phi, Yeah, like at the low energy Dirac fermion level is identical. Yeah. Yeah.
Really quickly, why is it SC4 not Z4?
Oh, that's a good question. So the Z4 center is identified with the U1 phase rotation. So basically, that's the Z4 center of the SU4 group. So it's actually a gauge operation and must be mode out. Yeah. It's in this CFT, one set of the scaling operators are the fermion bilinears, the fermion mass, and it is found that in these works that the fermion bilinears that include scattering across different channels, namely the flavor fermion bilinears, they carry the same quantum numbers as the competing AFM order on square lattice, namely the Néel order, where all the spins anti-align on neighboring lattices, or the VBS order, where neighboring spins form a valence bond, form a spin singlet. This theory unifies these competing phases at this CFT point. To go from the Dirac spin liquid to actually this ordered phase, we further need to confine the photons, as the Dirac fermions are already gapped by the fermion mass. And the confinement is caused by another scaling operator called monopoles. So in 2+1D, the monopoles are the instanton events that change the total flux of the U1 gauge field by 2 pi. For our purpose, all we need to know is that in this n equal to 4 QED, there are 6 degenerate elementary monopoles, and they transform in the vector representation of the SO6, which is identical to this SU4 mod C2 group. Three of them are carry the physical spin charge, so they are spin triplets, and the other 3 of them are spin singlet.
So this is 6 monopoles. It does have the center is located in different place. So maybe one is center located in the field of square, and another located in the link. How to understand there are 6 of them?
Oh, right. That's a good question. So, yeah, so it's discussed in this work from the state operator correspondence. The monopole are mapped to to a state with a 2 pi flux on a sphere, each Dirac fermion will, yeah, will fill 0 moles. Right. Yeah. So.
Why does it matter if the monopole is relevant? Because it's not a singlet anyway.
Sorry, why does it matter?
I'm just wondering, like, you say, like, elementary monopole relevant, but why does that matter if it's not a singlet? You can't add to the action to apply to the singlet.
Yeah, so that's, for the spin triplets, yeah, they all carry quantum number, but for spin singlets, they, under the UV symmetry, it's a smaller symmetry group than the IR symmetry, so it may be allowed. Right. Yeah, so in a previous work, we addressed the stability of the Dirac spin liquid concerning the monopole quantum number, like what kind of monopoles are allowed in the theory. And it is found that on triangular and Kagome lattices, there is no relevant symmetry allowed monopole operator, so this is actually a stable critical phase. While on square lattice, I want to, so in the next part of my talk, I'll make the case that there is one and only one relevant monopole operator, which is singlet, like allowed under the UV symmetry. And this singlet monopole operator is relevant by the large N expansion. So in this case, it describes a quantum critical point. If we have multiple symmetry allowed relevant operator, it describes a multi-critical point instead. Right. So before we discuss the detail of the QED perturbed by the monopole, so I want to make another connection to the high TC superconductor. So the phase diagram of the high TC superconductor is that at zero doping, there is an anti-ferromagnetic phase, and at some particular doping range, there is a superconducting dome. And it's also found that the superconducting gap vanishes at 4 Dirac points, so there is a nodal dispersion. Interestingly, we can also take the spin down and put them into a D-wave ansatz to describe a D-wave superconductor. So the procedure is to first make a mean field Hamiltonian for the spin down, where we include the spin down pairing that change sign under 90-degree rotation, corresponding to D-wave pairing. The mean field spin-down Hamiltonian, once we project onto the no double occupancy physical Hilbert space at finite doping, is supposed to describe a strongly correlated D-wave superconductor that accounts for the electron repulsion compared to a free electron D-wave BCS wave function. And at zero doping, namely at 1 spin-down per site, the low energy again has 4 gapless Dirac fermions. So actually, this mean field ansatz is gauge equivalent to the stagger flux mean field ansatz. So at zero doping, they describe the same physical state. This means that we saw that the Dirac spin liquid actually has like upon doping, this state naturally gives rise to the D-wave superconductor. Although it's still in tension with the phase diagram in last slide, where we saw that at charge neutrality is an anti-ferromagnetic state. So we'll also try to resolve this tension. Next we'll discuss the main part of the work, which is the kinematics of this QED theory when perturbed by the singlet relevant monopole on square lattice. So going from the UV to the IR, the symmetries in the lattice system are embedded into the emergent larger symmetry GIR through group homomorphism. And this is in general a non-trivial task. The parton construction provides partially this information, namely the projective symmetry group action from the UV of the partons will map into certain group elements in the IR. But there is also other complications involved with the Barry phase. And after some work, we found that on the square lattice, there is a trivial monopole under the UV symmetry group, which is a singlet denoted by formally by V2. This allowed monopole operator will drive the QED3 to strong coupling. And if you remember that all 6 monopole operators transform in a vector representation of SO6. So now one monopole condensation will break SO6 to SO5. To see what this does, it's informative to be reminded that there is a coupling between the fermion bilinears and the monopole bilinears, which is always allowed in the Lagrangian. And in particular, the terms that's involving this trivial monopole. So now the trivial monopole condense can be thought of as some C number, right? So these 5 terms are picked out, which effectively describe the coupling between the fermion bilinear and some other 5 monopoles. So this means that a particular 5 fermion bilinears is symmetry equivalent to the 5 uncondensed monopoles. And crucially, they just describe the ordered phase of Néel and VVS. There is some complication in that the monopoles are complex operators. So the 5 uncondensed monopoles have 10 components, and 5 of them couples to the fermion bilinear and transform as the 5-dimensional order parameter, and the other 5 of them couples actually to the 4 fermion terms, which is supposed to be more irrelevant. So we will focus on the first 5, namely the 5-dimensional order parameters. Right. So the spin Hall mass is not in the 5 like the 5 selected mass.
Operator there breaks time inverse, right? If time inverse of odd, spin Hall vector is time inverse of even.
Yeah, sorry, that's a good question. I don't have the answer on top of my mind. Right, so apart from the single relevant monopoles, there are other possible allowed local operators allowed by the UV symmetries. And we can group them in the representation of the IR symmetry group, which is SO6 cross the U1. And the tensor symmetric representation, which describes the anisotropy between the neo and VBS. And also some other like 4 fermion terms, another representation. They are always allowed in the lattice QED simulation. And the fact that the lattice QED see a gapless fixed point means that these terms are irrelevant, which is also consistent with the bootstrap result that if we plug in the relevant monopole scaling dimension and fermion bilinear scaling dimension, we will see that the scaling dimension of these operators are larger than 3 and irrelevant. And the other symmetry allowed operator are the double strings monopole, which according to a lattice Monte Carlo is above 3, so which is also irrelevant. And the excited monopole operator is also irrelevant from the larger N calculation. So we did a detailed analysis according to the symmetry representation and found that there is only one relevant operator on square lattice Dirac spin liquid. And the, as we say, the monopole condensate will break the symmetry group down to SO5. And this SO5 symmetry is actually anomalous in the sense that a instanton configuration of the SO5, which creates a vertex in one of the SO2 group, will carry a spinor representation of the other SO3 group. So this is nothing but the manifestation of the lattice Lipschutz-Matisse constraint. So namely the vertex of the SO2 group, which is the VBS order parameter, will carry a spinor of the physical SO3 rotation. Yes.
Just to comment about the double charge monopole on your previous slide. So I think it's probably much more likely that it's relevant because there's a bootstrap study by David Poland and some of his collaborators where with some assumptions they get an island, and the island they find is consistent with the large N expansion, which says it's relevant, and actually excludes the Monte Carlo estimate. I mean, of course, this is not a proof.
Right.
It's true that the assumption.
And the only unbiased computation is this lattice Monte Carlo simulation is the very large scale lattice.
Yeah, well, I mean,
that's the only unbiased computation at the moment.
I don't know if I would say it's unbiased. I mean, the lattice test that they use is a very unusual method, so I mean, it'd be good to maybe reproduce it.
Right. So for our purpose, if there is indeed a double strings monopole, then it's a multi-critical point. Yeah. So yeah, we need to base on the assumption that the double strings monopole is irrelevant. Yeah. But I mean, yeah, that's up to debate. Yeah, that's sure. Right. So this anomalous SO5 symmetry forbids a trivially gapped state, and formally is described by some like Stiefel-Whitney class. And actually, the full symmetry group, there is also a Z2 time reversal symmetry. And in this work, the authors show that this full symmetry group even forbids like gapped topological order. Right, so now we established, like, if we take the assumption that there is only one relevant perturbation in the square lattice Dirac spin liquid, and we are concerned with the actual fate of this, with this anomalous SO5 times C2T symmetry. And I'll argue next that the theory will flow to some symmetry broken phase that is independent of the tuning parameter. So this describes an unnecessary quantum critical point. So the possible fate, one can make conjectures. The first one is it still flows to some Gapless conformal field theory. And furthermore, in that strongly fixed, strongly correlated fixed point, if there is the relevant neo VBS anisotropy is relevant, then this describes the deconfined QCP on square lattice, which is not supported in the numerics. And the second scenario is that it spontaneous breaks time reversal symmetry and enters into a chiral spin liquid phase. Which is ruled out from the conclusion in this paper, which says that any problem that can be simulated in a sign-free manner, Monte Carlo, will rule out spontaneous time reversal breaking. Yeah.
How do you know this problem can be simulated with sign-free Monte Carlo?
Yeah, so
you don't have a Hamiltonian, right? So
yeah, so I guess that's yeah, that's a little like we can work with some like the spin-on configuration coupled to the U1 gauge field, yeah, and yeah, so it's at the point I can't say for sure that it can be simulated by a sign-free Monte Carlo. Yeah.
we're trying to involve something like the Gapless theorem.
Right. So that's just excludes any gap state, right? But you can have spontaneous symmetry breaking, I guess, for Lafave-Witten theorem, right?
Yeah, so I guess chiral topology of like this chiral spin liquid is just on the gap. But I don't know if the number of flavors is large enough.
I think the Lafave-Witten boundary
I guess here you can write down lattice gauge theory. Let's count on that in a while. With context. And then do a corresponding with flavor. Okay, it's really like a single one. And that, you know, is these people simulate that.
Doesn't that prove that population theory also applies to that form? That sounds
It's different from Lafave. This is a much more stronger statement. And Lafave is not from a lattice model, right? You could have terms of the lattice scale which are different. I think this is just a question about sign problem, free problem, that they can give you a chiral state.
yeah, well, I guess I'm saying that in QED3 with four player course, you cannot get that side by side quantum state.
Yeah, unless you put in terms that violate the sign.
Right. So we propose that the most likely scenario then is that it flows to some chiral, namely the flavor symmetry breaking states. And the symmetry breaking order doesn't depend on the sign of your relevant perturbation, so which renders it a unnecessary QCP. So to establish this argument, we add this trivial monopole to the Lagrangian, and as the anomaly of the global symmetry are Z2 classified, so the different signs of the perturbation will have the same global symmetry and anomaly. And it can be further proved that it can be further corroborated since the different signs are related by the by an SO6 rotation. The relevant perturbation in either direction will flow to the same order state. And the simplest scenario is that SO5 is broken to SO4. So we can, in the paper, we also argue against like the symmetry breaking in the, say, fermion pairing channel, and favored out that the symmetry breaking is in the fermion particle hole channel, as exemplified by the 5 fermion bilinears transformed in the vector representation of the SO5. And this symmetry broken state can be captured by a nonlinear sigma model with level 1 with Sumino-Wheaton term, which mapped the anomaly that we mentioned before. It's probably not surprising that this nonlinear sigma model also appears in the description that captures the Néel VBS fluctuations. So the SO5 vector will condense into a certain direction, and on the lattice system, the natural fate is that SO5 is broken into the SO3 spin rotation and the U1 as by the from the VBS operator rotation, and this is controlled by the anisotropy term between the Néel and the VBS order parameter. So as we mentioned before, so this term is irrelevant at the CFT fixed point. However, once we add this monopole, once the monopole fugacity is non-zero, it will become relevant and control the eventual symmetry breaking phase. So this is so-called dangerously irrelevant. And the sign of the anisotropy doesn't depend on the tuning parameter lambda due to the SO5 symmetry. So as shown here, this is a phase diagram in terms of the tuning parameter lambda and the anisotropy kappa. So at the origin, which is the putative unnecessary QCP, we have a relevant perturbation lambda, and the anisotropy term is irrelevant. However, once we turn on some monopole fugacity, the anisotropy term will first seems irrelevant, but eventually it will become relevant and determine whether we enter into the Néel phase or we are in the Néel or VBS phase. And either sign of the lambda doesn't affect the eventual ordered phase we are in. So the Dirac spin liquid hence is a unnecessary phase boundary inside this ordered phase. So this is like the liquid gas transition where, except that this is a continuous critical point. This codimension 1 manifold in the phase diagram will also end at some putative multi-critical point, which we also have some conjecture as the some mechanism for the multi-critical point. yeah, in terms of time, I'll just mention that we also have other unnecessary QCP examples in previous literatures, like in the non-abelian gauge theory at particular flavor number, and some in the context of interacting SPT, and some 1D model. The implication of the work is that if we go back to the high TC phase diagram, although the undoped case seemed to be an anti-ferromagnet, there is hope that inside the anti-ferromagnet we can tune close to the some Dirac spin liquid point, and such that when doping naturally gives a D-wave superconductor. So there is no need to actually tune out of the magnetic phase. And also the search in numerics for this Dirac spin liquid on square lattice do not need like too strong frustrated, the Hamiltonian with too strong frustration, since we can do it inside the Néel ordered phase. Sorry. Oh, sure, yeah. So I'll just briefly flash the another case of the Kavli SU3 antiferromagnet, where we realize the Dirac spin liquid as a critical point with 6 Dirac fermions. So we have SU3 fermions on each side, like 3 flavors of fermions, and at 1/3 filling with uniform hopping, the fermions also hit 2 Dirac cones for each fermion flavor. And at intermediate interaction strings, the system effectively is described by some spin Heisenberg model, where the spin again can be decomposed in this parton construction. We have a putative low energy theory of the QED with 6 Dirac fermions. Just to mention that at the strongest coupling limit, the system may form a valence bound solid where the 3 fermions around a triangular lattice will form some SO3 singlet. And at the non-interacting limit is electron system with describe a semi-metal with Dirac dispersion. And at this intermediate regime, there are 20 elementary monopoles, and we find that in the one of the SU3 singlet monopole is trivial and also relevant from the larger nav calculation. We can also, if we propose that there is no other higher monopole, relevant monopole, which is supported by large N calculation, and then the Dirac spin liquid on this SU3 magnet also describe a quantum critical point. Crucially, there is no LSM in this case. We have 3 particles per unit cell for SU3. The 't Hooft anomaly is generally present once the trivial monopole proliferates. So it rules out the possibility that it can flow to some trivial gapped phase. The detailed fate of this theory remains elusive. So this will be the summary of my slides. Yeah, thanks.
Questions?
Quick question. The parameter lambda needs to be real because of time reversal or something like that? The monopole fugacity?
So we only have one real component monopole that's trivial, right? So the trivial monopole is a real component. Yeah. So it's already Hermitian. So
that's M plus M dagger. What about
Yeah. So only say with a particular phase choice, you can say only M plus M dagger is trivial, while basically the real part of M is trivial, and the imaginary part change sign under time reversal.
I see. Thank you.
Any other questions?
So just so that I understand, so the square lattice at the center of your phase diagram, where you have this multi-critical point, that has SU4 global symmetry then. That's so you're claiming that there's an SU4 global symmetry at PQCP. That point there.
And at this point.
Well, this one here. Okay, so yeah, that point, that has SU4 symmetry then. Is that correct?
Yeah, if you tune the fugacity to 0, associated.
So you're saying that critical point has SU4 symmetry. So yeah, my other question, which I think you implicitly assume the answer is yes, but I want to be sure, which is that is it known from bootstrap or simulations that SU4 theory exists on its own without, even if you suppress the monopoles, is it fully established that it exists?
Yeah, I think there is lattice Monte Carlo that simulates this QED without monopole, and it flows to gapless state, like it stays gapless by like Karthik and Nair.
And Shai, the bootstrap also agrees with that, or no?
So there are predictions for monopole operators.
No, let's assume the monopoles are not there.
Obviously, just the existence of theory.
Yeah, and if it...
It's hard to prove that a theory exists with bootstrap, you just get found.
Yeah.
Like the evidence for bootstrap, basically, there was first this paper with Dean Silju 10 years ago, where we found the large N estimates were right near the boundary, which is usually a good sign. And then there was a follow-up paper where Poland and collaborators were, with some assumptions, which may or may not be true, we were able to get an island kind of consistent with the large N values. So it seems promising, but I wouldn't say it's...
Okay, thank you.
Thanks.
So, is there any way to distinguish which side of the Dirac spin liquid you are on when you are in the new phase? Say, is there any way to distinguish whether lambda is greater than 0 or smaller than 0? So, if you are tuning within the new phase, how do you know that you have already crossed the critical point numerically?
Right, so the critical point, thanks for the question. I skipped this slide. So the critical point will have signature in the physical observables, namely the order parameter and the spin stiffness will vanish as a power law as you tune cross the critical point. And for the VBS, the gap will also vanish. So that's the usual like quantum critical fan story in like cross-phase transition. Yeah.
Is there any concrete proposals for the lattice model that realizes this?
No, we don't have, As we say, this only says that we don't need too strong frustration to search for Dirac spin liquid, as they can exist inside the antiferromagnetic ordered phase.
Okay, thank you.
At the end, you mentioned doping this unnecessary Dirac spin liquid quantum critical point will lead to some superconductivity. Can you clarify that?
So this is because the spin now, the stagger flux ansatz is gauge equivalent to the D wave ansatz. And from the usual like parton story, right? Once we doping, one can add in some holon, and then the holon condensation will translate the spin-on pairing into the electron pairing, like the D-wave pairing for the electrons.
I thought here for this D-wave thing, you need what gauge structure do you need?
U1. I mean the mean fields, the mean field ansatz. There is a U1 gauge group that's like, invariant under U1.
Okay.
I can comment if you don't mind. So if one does this, you go out of the staggered flux, this state into by condensing charge-ons, then the charge-on, they turn out to be two-component charge-ons from the PSG of the staggered flux phase. And this was worked out by Nagosa and Lee, and you should be the one talking about. then you have to look at the quartic terms in the Charge-on-Hamilton Lagrangian, and depending on various parameters, it either goes to a D-wave superconductor or a spontaneous current phase. There are two possibilities.
Oh, I see. Yeah. Thanks.
Any other questions? If not, let's thank the speaker.